At 9 a.m., the system was working fine. At 9:30 a.m., a few long-running requests came in. Suddenly, even the simple request started getting slow. At 10 a.m., the system was down. There is a simple architecture that could have helped prevent this: web queue worker architecture. It's a simple yet powerful architecture that breaks your system into three components: web, queue, and worker. The web service receives incoming requests. The worker handles long running or resource intensive tasks in the background, and the queue provides asynchronous communication between these two components. This is the basic idea, but to really understand why this architecture matters, let's uncover what actually happened inside the system during that 1 hour. This was the monolith. It usually receives a large number of small requests from clients. Most of those requests are simple and they take only a few milliseconds to process. But along with these small requests, the same server also receives some long running requests. These requests take more time, they consume more CPU, and they keep the server busy for longer. That day at 9:30 a.m., the system received a higher than usual number of those long running requests, and they were highly CPU intensive. The CPU usage went high, the server became busy, and then even the small requests started waiting. The requests that usually finished in milliseconds got stuck, and finally the system crashed. Now, the question is, what's the fix? How can we avoid this in the future? The fix is simple. We offload the heavy work from the front server. The web receives the request. It checks whether the task is small or long running. If it is small, the web handles it itself and returns the response. If not, it passes the task to the worker. Now, even if CPU usage goes high because of those heavy jobs, the web server is not impacted. It can still stay available to handle new incoming requests. This improves both availability and performance. The web sits in front and handles incoming requests. The worker sits in the background and processes long running tasks. But why the queue? What role does the queue play? It enables communication. The web communicates with the worker through a queue. But again, why a queue? Why not just use an API call? Because an API call is usually synchronous, but a queue makes the communication asynchronous. And this is a key decision in web queue worker architecture. If we used an API call instead, worker failures could cascade back to the web, and that could break the whole setup. Let me show you a scenario to explain this. The web server receives a request. It tries to pass that request to the worker using an API call. But the worker is already slow because it is processing some long running task. So the web server keeps waiting. After 30 seconds, the request times out. Then it tries again. Meanwhile, more long running requests keep coming in. The web tries to send those requests to the worker as well. They also wait, they also time out, and they may also get retried. The requests start piling up on the web server. The worker is already struggling, and now the web server also starts running out of resources. This is how failures can cascade from one service to another when we use synchronous communication. In the end, the web server can become unavailable too. So, what was the point of offloading long running tasks if the same failures can still come back and take the web down? That's why we avoided API and used messaging or queue. In case of a queue, the web server does not wait for the worker. It simply puts the messages in the queue and sends an acknowledgement to the client. If the worker is available, it picks the message from the queue and processes it. If the worker is not available, the message stays in the queue. Whenever the worker becomes available again, it picks the message and continues processing. The web server does not even directly know the worker. It is no longer responsible for delivering the task to the worker. The queue takes over that responsibility. This is how the queue allows them to communicate in a loosely coupled way, and that is how it helps prevent failures from cascading. Now, there is another important implementation detail: communication between the web and the client. Previously, it was simple. The client sent a request and the server returned the response right away. But now the scenario is different. For long running tasks, the web server only sends an acknowledgement first. The actual result comes later, once the worker finishes the job. Usually, the web returns a job ID to the client, so when the result is ready, it knows which request it belongs to. Now, once the task is done by the worker, we need a way to tell the client that your task is done. How can we do that? One option is polling. where the client keeps checking the status of the task. Another option is long polling. It is similar to polling, but here the client sends a request and the server holds that request until the result is available or the request times out. If it times out, the client sends another request. This continues happening until the result is ready. And the third option is WebSocket, where the server pushes the result to the client as soon as it is ready. So, what do you think? Which approach is the best? Polling, long polling, or WebSocket? Write your answer in the comments, but think carefully before you answer because this is a tricky question. Now, let's discuss a reusability concern. We need two independently deployable host projects, web and the worker. But when you implement this, you may notice that both projects often need the same business logic. So, wherever it makes sense, you can share and reuse the business logic. For example, in Visual Studio, you can create two separate host projects and let both projects reference the same shared business projects. This keeps them independently deployable while still reusing common code. The next concern is the database. Should both hosts use the same database or should they use different databases? In most cases, you may start with the same database. It is simpler, has less overhead, and makes reuse easier. But in some advanced scenarios, different databases may make more sense, especially when the worker is running database intensive jobs. Let me explain. Remember why we introduced WebQueue Worker? Because we do not want long running resource intensive tasks to bring the whole system down. Right? Now, suppose the web and worker are sharing the same database, and the worker starts running heavy jobs that use the database intensively. What can happen? The database may slow down. And since the web is also using the same database, the web gets affected too. So the failure can skill cascade back to the web, but this time through the database. To avoid this, we may need a proper bulkhead. If you do not know the bulkhead pattern, I have a separate video on that. In this case, if both the web and the worker used separate dedicated databases, the problem in one area would not cascade to the other. Moving from a monolith to a WebQueue worker architecture may seem like a small step, but it opens all the door towards a more modern distributed architecture. It can become your first logical step towards microservices or cell-based architecture or some other form of more advanced distributed system. Why? Because it gives you the same building blocks on a smaller scale. Separate deployable components, messaging, and asynchronous communication. And messaging is often the backbone of many real microservices systems. It also introduces similar challenges like request tracing, message ordering, or duplicate messages. You start seeing similar patterns and tactics like retries, idempotency, load leveling, competing consumers, and bulkheads. And you also get similar benefits like independent deployability, fault isolation, and independent scalability with different elasticity. For example, you may only need just two servers for the web, but five for the worker, which can even scale out more aggressively when the queue builds up. In short, WebQueue Worker use the same building blocks on a small scale that are used in microservices and distributed architectures on a larger scale. If you like this video, check out my channel for other software architecture videos. I'm trying to build a full journey from developer to architect and beyond.